So, welcome back. We have listed in the last session the set of inference problems that we will address. The problem of class equivalence, subsumption, disjointness, consistency, global consistency is the whole knowledge base consistent, and instance checking essentially. So, let us look at that problem. To find out whether a class C is equivalent to a class D, show that this is a logical consequence of the KB. So, this is true if both these things are true. We have already said that. We break it down into subsumption checking. So, this problem is called subsumption checking. This is a key thing. You want to show that C is subsumed by D, and we have already said that this statement we will reduce it to this statement, not C union D, and then we will take its negation and add it to the knowledge base, and we will show that the knowledge base has become unsatisfiable. And when we simplify this statement, when you push the negation side inside, we get C intersection not D. So, what does C intersection not D look like? When C is subsumed by D, if this is D, if this is the universe of discourse, and if this is C, then not of D is this, everything that is outside D. So, this is the set that I have drawn here. So, can we find something which is in this set essentially that we cannot find an element here. On the other hand, as we said earlier, if this is this thing, then the negation of this thing was this set. Okay, so, you must remember that this is empty, because C does not have an overlap with not D. Not D is the shaded portion outside, and C is the shaded portion inside essentially. But when we so this was C and the other thing was not D, and you can see there is no overlap, I think. Now, you can see that this region so this was C and this was D, then C intersection not D. Not D is everything which is outside D, and if you intersect it with C, you get whatever is common with C, and you can see that this is not empty. So, if C is not subsumed by D, then C intersection not D would be satisfiable, because it is a not empty set and an element may exist in that. Whereas, if C is subsumed by D, then what we will get is an empty set, and there is nothing that can be in an empty set. So, that is not going to be satisfiable. So, that will be unsatisfiable. So, that kind of explains the rationale behind taking the sentence like C is subsumed by D and replacing it by this sentence that show that this sentence is unsatisfiable, or the negation of that sentence is unsatisfiable. To find out whether two classes C and D are disjoint, show that their intersection is empty. So, remember that this stands for the bottom concept, which is also the empty set, is a logical consequence of this. So, this is the knowledge base entails that C intersection D is empty if you assume that there is some element A which belongs to this class C intersection D, and then that becomes unsatisfiable, that there is no such element essentially. To find out whether a knowledge base is globally consistent, we will essentially say that there exists some element somewhere in the domain, and if that is satisfiable, then the knowledge base is globally consistent, where A is a new individual not already mentioned in the knowledge base. To find out whether a given class C is consistent, show that C is not an empty set. So, this stands for C is subsumed by the empty set, which means C is an empty set, is not a logical consequence of the knowledge base essentially. If it is not an empty set, then it will have some element, and that means it is satisfiable. So, C is consistent if this is satisfiable. On the other hand, C is inconsistent if this whole thing is unsatisfiable essentially. So, to show that C is unsatisfiable, if you add the C of A, where A is a new individual again to the knowledge base, and then show that that is unsatisfiable. To find out if an individual A belongs to a class C, show that C A is a logical consequence of K B. So, this is what you want to show, and what you do is you add the negation of that to the knowledge base and then show that it is unsatisfiable. To find all individuals that belong to the class C, you collect all individuals from the domain. Remember that this stands for the domain or top class or thing essentially, such that C of A is entailed by the knowledge base. So, you just collect all those individuals together. Now, like the tableau method that we studied for propositional logic, the tableau method for description logic is similar, that you have a set of expansion rules. You start off with a root node and then you keep applying this expansion rules. The root node will contain all the A box statements, and then you apply the expansion rules and then try to show that there is a model. If the process of extending the tableau terminates in the sense that you cannot apply any more rules and there is no contradiction, then it is satisfiable. But if all branches are closed, then it will be unsatisfiable, exactly like what we did in the tableau method for propositional logic, except that the rules here are as follows. There is the intersection rule, the union rule, the there exists rule, the for all rule, and the T box rule. The T box rule basically says that whatever you have said in the T box, which is true about the domain, will apply to the individuals that you are talking about. And remember that we start constructing the tableau by individuals which we have taken from the A box. So, we construct a directed label graph as before, which is called a completion graph, where V is a set of constant variables, E is a set of role assertions, and L is a set of node and edge labels. So, these are the node and edge labels. So, a node label says that this element X belongs to some concept which will be listed in this list essentially. So, it is a list of concepts. Likewise, there is a list of roles for which pairs of elements are listing. So, if the label for role label for Lucy comma X is likes or by, it basically means that we have Lucy, we have X, and the relation is either likes or buys or both in this case. So, Lucy likes X, Lucy buys X. The label set for a individual are the concepts that the individual belongs to. So, in this case Lucy is a teen, and also that Lucy is someone who likes fruit essentially, and X could stand for fruit, for example. Now, this one rule, the union rule, creates branches in the proof procedure, just like the OR rule in propositional logic creates branches. This also creates branches in this thing. So, the process would basically be, you follow one branch, expand a branch, and when a contradiction or a clash occurs, we will define what we mean by this. That is, you have A and not A, two concepts in this thing. They belong to the label set for X, or bottom belongs to the label set of X, then backtrack and try another branch. So, essentially we are looking for a satisfying assignment or a model essentially. A branch is closed when a clash occurs, which basically means it has something like A and not A inside, and a branch is complete when no more rules can be applied. So, the algorithm is going to be convert formulas to NNF, prepare the T box and the A box, and initialize the completion graph with elements from the A box. So, as we said that we start constructing the tableau by elements from the A box. Apply all T box axioms to all individuals, because that is what the T box says, that these are generic things which apply to everything in the domain. And if there is a contradiction, then backtrack and try another branch, if you are looking at this rule essentially. So, either you will have some closed branches or you would have some complete branches. So, when a tableau returns a clash free completion graph, then the input sentences are satisfiable or consistent, which means there must be at least one branch which is clash free. Then we have a model, and then we say that the sentence is satisfiable. If it fails to return a clash free completion branch, which means there are no branches which are clash free, then the original set is unsatisfiable or inconsistent. So, let us look at some of these rules here. This is the intersection rule. If this concept belongs to the label set of X, so we are looking at a node in the graph. So, somewhere there is X, and X may be a child of something else, and so on. And C and D do not belong to this label set, then we add this C D to the label set. So, for example, if we started with C intersection D, then we add C and D. So, we have these two new things added to the label set of C. So, this follows from the meaning of intersection, that X belongs to the class C intersection D means X belongs to C and X belongs to T. So, again we are trying to eliminate operators, just like we did earlier. If one of them happens to be already in the label set, it does not matter, we add the other one to the label set. For the union, if we are saying that X belongs to C or X belongs to D, or both of course, and if C and D are not in the label set, so their intersection is empty, then you create two branches, branch 1 and branch 2. To one you add C and to the other you add D essentially. So, if you had this X with the label C union D, then you take two branches, to one you add C, to the other you add D essentially. We are still talking about X here essentially. if one of the two concepts is already there in the label set, then the union rule does not apply, because we already know that it belongs to C. So, that is enough to tell us that it belongs to C union D essentially. The existence rule, if in the label set we have there exists R C. So, remember what does this say? This says that there exists at least one role filler who comes from the class C essentially. So, it is a role filler who comes from the class C. So, X is related to something and that something comes from the class C. So, and there is no Y such that X Y belongs to the such that R belongs to this pair X Y, that the edge X Y is labeled by R and Y should be labeled by C. Then we add a new variable Y. So, we started with X, then we add a new variable Y and we have this relation R here, and we say that Y belongs to the set C. So, if we have this statement there, then we add a new edge and we say that Y belongs to C. So, the universal rule now, if this statement which says that all role fillers must come from the class C, then remember that the universal statement is conditional, that if there is a role filler, then that role filler must come from class C. It does not say that there has to be a role filler. So, that is what we are saying here. If there is a Y which is a role filler for this R and C does not belong to the label set for Y, then add C to the label set for Y essentially. So, if we have this and if we have a role filler R and C does not and Y does not belong to C, then add C to the label set of Y essentially. So, for every edge that is emanating from X, we must do that. So, if there is a X here and if we have a Y here and a Y1 here and a Y2 here, all of them are related by this role R. Then for each of them we will check whether C is added as a concept. If not, we will add it as a concept. The T box rule, as we said, that if there is any T box statement and it does not belong to the label set of X, then add it to the label set of X, and this is because T box statements are general statements that should apply to every individual. We do not apply T box rules to closed branches, we will talk about that in a moment, and we do not apply T box rule to blocked variables. So, closed branches are when they are inconsistent and we do not need to extend them any further. Blocked variables are variables which could potentially go into an infinite branch, and we want to nip that in the bud, as we say. So, apply all T box statements to all individuals, that is the basic idea of the T box rule. So, let us say that we have in our knowledge base a sentence which says there exists at least one role filler from the class C, and we know that there is an element A which comes from the class C. So, is this satisfiable? Is there a model for this? So, how does it work? We start by constructing the A box as the starting point of the tableau, and so A is in the A box. So, our first sentence comes from there, that there is an element A and which belongs to the class C. So, C is in the label set of A, and then we have one T box rule. So, we need to apply that to that. So, we bring it here, apply T box rule, and what does this rule say? That create an x1. So, this A create an x1 such that x 1 is related to A by the role R and give it a label C. So, we started with A belong to C, but that does not matter. We also want to say that there exists a role filler of the class C. So, we create this x 1 and we say this also belongs to the class C. So, belongs to C. So, let me use belongs to here. So, now we have this statement that there is this x 1 which belongs to the class C. Now, again we have to apply the T box rule, because that is what the method says. So, we have to either keep applying till no more rules apply, or if a branch is closed, but in this case neither will happen, and therefore, we will have to invent a method for stopping this expansion process. So, we started with A, then we added x. Now, we are saying that add an x 2, add another variable x 2, which must come from the class C. Everything is from the class C in this example here. So, x 2 must be from the class C and x 2 must be a role filler for x 1 essentially. So, you can see we started with A, we added x 1, we added x 2, then we will add x 3 and so on, and we do not want to keep doing this essentially. So, this is where we define the blocking rule essentially. So, if a rule induces a new variable, then applying the same rule to the new variable may induce yet another new variable. That is the problem that we just saw, and it may not terminate therefore, essentially. So, we can force the tableau to terminate if we block the variables from creating new variables that are similar. So, by similar we mean they have the same label set. So, in this example x 2 can be blocked. So, a node x blocks node y if y is a variable and not an individual, it cannot be a constant, and x is the ancestor of y and the label set of y is contained in the label set of x. So, any x with the label set x y is a predecessor of y, because y is a role filler for x. Every predecessor of y which is not an individual is an ancestor of y. Every predecessor of an ancestor of y which is not an individual is also an ancestor of y, and a node y is blocked if it is directly blocked or one of its ancestors is blocked. So, that is the definition of blocking. So, basically we stop this unending chain of new variables being created, and then of course, once we have blocked it, we do not expand that branch any further. Okay. So, let us take a break and we will come back and look at some examples.